Alright, so let's talk about some triangle congruence theorems and postulates and whatnot. Anyway, most of them involve either S or A. S is for sides, A is for angles, because that's really the main two things that triangles have. So, there are 8 different ways that we can put this together. Let's kind of write those out. So first is SSS, then there's SSA, then we could have SAS, and how about SAA? Then we could have these same things with A in front. We won't write that one. And then ASA, and then AAS, and AAA. Now, some of these work with triangles and some do not. So let's see if we can figure this out as to whether or not we can kind of use this as a theorem or postulate to prove that triangles are congruent. So let's start with the first one because it's a great place to start. So let's make 2 triangles that have the same 3 sides. So there's one triangle, and here's another triangle. And I'll do my best to draw these to scale, but I'm not an artist, so I'm not so great at it. Anyway, where I lack in artistic skill, I know in notation. So what I'm going to say about these 2 triangles is those are the same, just by putting 1 tick on them. Let's say these sides are going to be the same by putting 2 ticks on them. And let's say these sides are the same by putting 3 ticks on them. So the whole idea behind this is that the theorem says that if, so let's say if, now we'll write this out, we won't write out the whole thing because the whole idea says that if 3 sides in 2 triangles are congruent to if 3 sides in one triangle are congruent to 3 sides in another triangle, then the 2 triangles are congruent. But we're just going to say if 3 sides of one triangle are congruent to 3 sides in another triangle, then the triangles are congruent. Let's say the triangles are congruent. A little shorthand, because my writing's terrible. Anyway, this is true, because if I were to use the same 3 sides to build another triangle, these 2 triangles have to be the same, and that's the way it is. That's provable. So there's that. That's one of them. So this one's good. So how about SSA? 2 sides. Now these are written very specifically. So SSA means that I have 2 sides and an angle that is outside of those 2 sides. So for instance, let's say that I have this side, that side, and this angle. So this angle doesn't have a side attached to it. So I'm going to use a dotted line to show that. And actually, I don't want to use that diagram. Let's try it again. Let's say I have this side, that side, and some angle here, but there's no specific side attached to that angle. So I'm going to just draw a dotted line there. Now, the problem with side-side angle is that I can draw this. So I have this side, and that angle. That's SSA. Because I have 2 sides and an excluded angle. The key with this one is the angle is not in between the 2 sides. We're not talking about this angle. If we were talking about this angle, we'd be talking about side, angle, side, because the angle would be in between the 2 sides. But I'm not doing that. I want the angle that's outside of the 2 sides. Anyway, I can draw the same diagram if I have this side, and this angle. Now, again, this isn't going to look very pretty. But let's pretend that these 2 sides are the same, this side's the same, and these angles are the same. This still makes the same triangle. Well, it doesn't make the same triangle. That's the idea, that this one does not work, because these are absolutely 2 separate triangles. This angle is very different from this angle. This is an obtuse angle, that's an acute angle. Now, there is a very special instance where this works, and we're going to talk about that later. Anyway, SSA and angle side side are essentially the same thing. One's just the other one backwards. So we can actually cross out 2 of these at the same time. So there's two of them. If two sides and an excluded angle of one triangle are congruent to two sides and an excluded angle of another triangle, we cannot say with certainty that the triangles are congruent. Now they may happen to be, but would have to use some other form to prove that. Anyway, let's move on. Side angle side. So if I'm doing side angle side, I have one side of one triangle and an angle. So I have this side, an angle, and another side. And I have another triangle with the same side, the same angle, and the same side. So the question is, knowing this, is there any other way that I can create a line there? And the answer is no, that if I have two sides and an included angle, now two sides and an included angle means that these two sides make that angle. That is the included angle between these two sides. So I can write a conditional statement about this saying that if a side, an angle, and a side, if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. Because there is no other way. If this, and that is locked in and I cannot change those three pieces of information, there's only one way that I can draw this third line. Now if we go back and use that same thing with this side-side angle, then I mean this side can kind of like hinge because this angle isn't set. So this side can kind of like spin around and this works and that works. That's two separate triangles that have the same properties, but they're absolutely not congruent. So side angle side does work. So we have two of them so far. So let's keep going. The next one is side angle angle. So side angle angle says that I have one side and two angles. So let's see. I have a side here. So we have a side and we have an angle and another angle. So what's interesting here is that this is set and this is set, but I really don't have those sides yet. What I have, oh, you can't even see that. Oh, there you go. So I have this side, this angle, and that angle. What I don't have is really, I don't have these sides. So what I could actually do is take this angle and pull it out, but what happens if I pull that angle out? If I pull this angle out, it's going to become acute. If I were able to pull this angle out really far, and so it would look like that essentially, this angle is much smaller than this angle. So that angle changes. So I can't actually move this because if I pull this out, it gets smaller. If I push it in, it gets bigger. So by moving this angle, it's actually changing the size of that angle. So this one really can't move, but this side can change, that side can change. Under only knowing that we have a side, an angle, and an angle, technically these two sides can change. But if I change these sides, this angle changes, which I'm not allowed to do because it's set that I know this angle, and I know that side. So with all of these set, it actually pretty much, you can almost think of it as solidifying the triangle. So if I know another triangle with these same properties, and I can even draw these in because we said that those sides can't change. If I know this stuff, then this is another postulate that if I have a side and two angles, then the triangles are congruent. And that's another congruence postulate. So side angle angle works. Now you might notice that angle angle side is the same thing. Generally speaking, we call this one angle angle side. However, side angle angle is logically the same thing. So it doesn't truly matter which one you use. However, generally mathematicians use angle angle side. So anyway, how about angle side angle? So with angle side angle, I have some known angle, some known side, and another known angle. So I know this angle, this side, and that angle. Now this is similar to side angle side. With side angle side, I had a side, an included angle, and the other side. With angle side angle, I have an angle, the included side, and another angle. So what can change in this? Well, this angle can change, But this angle can't and this angle can't. I can't draw these other two sides any other way without changing either these angles or that side. So with this information, I can construct this triangle, and if I draw any other triangle with these same properties, with this angle, that side, and this angle, these two triangles have to be the same thing. So I can write a conditional about it, that if I know an angle, the included side, and another angle of a triangle, and they're the same with a separate triangle, then the triangles are congruent. And that's a bad swoop. There, that's better. Which gives us another one, angle, side, angle. Cool. Last one, angle, angle, angle. Angle, angle, angle. Now, angle, angle, angle is, so let's say, and I can draw this. This one's pretty easy to do. In fact, I can use a specific triangle to show you this. That let's say I have an equilateral triangle where I know all three angles are exactly the same. In fact, in an equilateral triangle, all three angles are 60 degrees. Now I can draw another triangle, another equilateral triangle, where all three angles are 60 degrees. These are two triangles with three congruent angles, meaning this side, and this side are the same, and this side, and this side are the same. These are three, why do I keep saying three? These are two triangles with three congruent angles. And these triangles are absolutely not congruent. Let's say this side is 3, this side is 3, and this side is 3. This side's maybe 12, this side's 12, and this side's 12. These are not congruent. Congruent is they are the exact same thing. And if they're the exact same thing, then they're congruent, but these are very different. Only the angles in these triangles are congruent. The sides are not. Therefore, angle, angle, angle does not work. So we have 5 circled here. However, remember, these two are pretty much the same thing. So I can make a list of 4, and we're going to add to this. Side, side, side. Then there's side, angle, side. Then there's angle, side, angle. Then there's angle, angle, side. And there's 4 of them. Now there is a 5th one. So let's talk about the 5th one. And the 5th one has to do with angle, side, side. Angle, side, side, or side, side, angle. It's one of these. Because I can actually draw that there's one instance where this works. And this works specifically when you're dealing with a right triangle. Because let's say that I have to have a right triangle. If this is a right triangle and I know this side and that side, there is actually only one other triangle that I can draw with the exact same pieces. And I could show you this very, very specifically. But if this has to be a right angle, we said it doesn't work if this angle is weird. But turns out if this is a right angle, if this angle is a right angle, which it obviously isn't, if this angle is a right angle, then this line, this leg that we said before that could move, it can't move anymore. Because it's just touching this side. So where we knew, so now we know this angle side side, it's a little different of a setup, that this actually works. This looks like angle side side or side side angle in reality, so we don't write bad words on our tests. Instead, we write it as if HL, hypotenuse leg, which are two special pieces of right triangles. So if hypotenuse leg, then the triangles are congruent. With hypotenuse leg, we are told that, well, in a right triangle, first of all, identifying some parts of a right triangle. If I have a right triangle, just some right triangle, and that's a right angle, then that just looks terrible. I mean, this isn't much better, but here we go. If this is a right triangle, then this side is the hypotenuse, this is a leg, and that's a leg. So every right triangle has one hypotenuse and 2 legs. And that's what they're labeled. So if I know the hypotenuse and one leg of a right triangle, and I know that the hypotenuse and leg of another right triangle are the exact same thing, then these two triangles have to be congruent. And those are now the 5 congruence theorems and postulates for triangles being congruent. And we'll stop this video there.